Yes, Nabila. No. We so how to conduct it? Even the presenter is not there. Without Q&A? Okay. Okay. So how would it be if the presenter is coming later on then? Okay. Sure. I cannot attend. Okay, okay. Okay. Okay, just we are starting with Dr. as one student, then Hamad, right? Right. Okay. 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 I cannot see the green room. I cannot see the green room. Yeah. So I'm not through. I'm not through so far. Okay. Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. And good afternoon to everyone, or good morning. It's depending on where you are. So, welcome to the first parallel session on advancement in drilling operation and automation in Icoget under ESCON 2020. First, let me introduce myself. My name is Asif Zamir from University Technology Petronas. I will be the chair for this parallel session. So, without further ado, let me begin with the first presentation. So I'm glad to welcome our first presenter, Mr. Abdul Hazim Abdullah from University Technology Petronas. Hazim will be talking about the optimization of cutting parameter of a single polycrystalline diamond compact cutter at small depth of cut and low back rack angles in cutting selected rocks. Please welcome our first presenter.
Assalamualaikum and a very good morning to the chairman, co-chairman and audiences. I'm Abdul Hazim, a postgraduate student from University Technology Petronas. Will present research findings entitled Optimization of Cutting Parameters of a Single Polycrystalline Diamond Compact (PDC) cutter at small depth of cuts and low barrier angles in cutting selected rocks. This presentation will be conducted according to this outline. I will present the research background, problem statement, and objective in the introduction part. Then the research materials, experimental setup, and design of experiment will be presented in methodology section. After that, I will present the result and discussions obtained through this study. Lastly, the presentation will be ended with a conclusion. The drill bit consisting of several types and the PDC bit was under feed scatter type. It should be noted that the market sharing for PDC bead has increased in recent years. Thus, we focus on the improvement of PDC bead due to its wide application in oil and gas industry. Replacement of the PDC bead occurred when its cutter has become worn. PDC cutter influenced the drill ability of the bead and contributed to the overall drilling cost. Studies have been performed using single PDC cutter rod intervention to enhance the performance of the bead. This study will be focused on a single PDC cutter as the main element in influencing the bead performance. In this study, we focus on single PDC cutter rod intervention for a few reasons. First, due to lower cost of equipment and operation, we are also able to diminish complex cutting conditions in whole PDC bead studies and make it easier to control cutting parameters. Lastly, the understanding of single PDC cutter rod intervention mechanism helps engineers to get a vision into the cutter improvement. Based on the literature review, we found that different rock properties exhibit different formation and sedimentation characteristics might influence the result of a single cutter rod intervention study. In addition, we also realized there is a lack of optimization study of cutting parameters on cutting force for single cutter rod intervention studies. Therefore, the objective of this study is to evaluate the effect of cutting parameters on cutting force using different rod types. Second objective is to optimize the cutting parameters subjected to minimize the cutting force when cutting Carthage marble and Indiana limestone rock formation at the small depth of cuts and low barrier angles. Moving on to the methodology section, we utilize two types of rock samples which are Indiana limestone and Carthage marble and differ by their properties. The PDC cutter used in this study has a thickness of 2 mm diamond layer and a 6 mm carbide substrate. The rock cutting experiment was conducted using a conventional lathe machine and consists of several main components. PDC cutter attached to the cutter holder. Rock samples were attached using a 3-jaw chuck. The force measurement was done by using a series of equipment to produce a cutting force graph for further analysis. Next, three factors, depth of cut, barrier angle, and rock properties were employed at 3 and 2 levels as shown in the table. We repeated the experiment for each combination 3 times for better accuracy of the results and to minimize the human error. In total, 54 experiments were performed. The first part of the result is the analysis on the cutting force mechanism. All the graphs of cutting force show a similar trend and one graph was chosen to assess the mechanism of rock cutting. From this graph, we divide into 5 phases. We want to highlight that in phase 2, the cutting force measurement reaches a maximum value and recognized as a stable phase. Based on ANOVA, all factors of the depth of cut, barrier angle, and rock properties and their interactions had a significant effect on cutting force as their p-value less than 0.05. We also obtained R-squared and adjusted R-squared at 0.9874 and 0.9857, which is close to maximum value of 1. By using this statistical analysis, we also obtained 2 mathematical models according to the specific rock type. We will be able to employ these models for predicting the relationship between process parameters and force. This 3D graph was produced to assess the effect of depth of cut and barrier angle on the force. We can observe that the depth of cut and barrier angle had a significant influence on the force in Carthage marble cutting. Moreover, at a low depth of cut at 0.5 mm and high barrier angle at 15 degrees, the influence of the parameters on the force was the lowest. Then the force increases steeply with increasing depth of cut and decreasing barrier angle. We recognize that the increment of force with increasing depth of cut is due to the contact length between the cutter and rock. The contact length of the 1.5 mm depth of cut is higher as compared to the 0.5 mm depth of cut as illustrated in the figure. Since the contact length is larger, the contact area between cutter rock also increase and cause friction and force to be much higher. For the effect of the barrier angle on the force, we can observe that the trend of the graph was contradicted with other findings. Based on the illustration, the contact area of cutter rock in 15-degree barrier angle is larger than 5-degree barrier angle at a constant depth of cut. Theoretically, when the cutter rock contact area is larger, the cutting force will be higher as more volume of rock sample needed to be removed. On the other hand, in a similar experimental setup with our study, Chair indicated that the effect of barrier angle on cutting force is non-linear. The cutting force result is upside down as the barrier angle increased from 10 degree to 25 degree. But it is reminded that their studies only involve the barrier angle higher than 10 degree and it is still a question on how the lower barrier angle than 10 degree affect the cutting force. There are several reductions on why the cutting force decreased with increasing barrier angle. Firstly, we look at the cutting action and crush rock sample at a very low barrier angle. At a very low barrier angle, the cutter is more becoming to pushing action. It is considered when the low barrier angle cutting the rock sample, it is harder for the rock to be crushed into chips due to the addition of pushing action of the cutter. At a high barrier angle, it is easier to form the chips and the cutting force needed to do the cutting is lessened. Thus, more cutting force is needed to cut the rock sample at a 5-degree barrier angle as compared to a 15-degree barrier angle. The other deduction is to look at the flow regime of the rock as the cutter cut through the rock sample as described by Akbari. As the flow barrier angle increases, a resultant downward force causes a portion of the rock material to flow underneath as shown in the figure. In this way, chips flow easier and reduce the cutting force acting on the PDC cutter. In addition, when the PDC cutter cut the rock sample at a very low barrier angle, the crushed rock accumulates at the face of the cutter and did not flow underneath the cutter, cause the mass of the rock to increase. This condition caused the cutting force to be higher at lower barrier angle. For Indiana limestone cutting, the depth of cut and barrier angle had an insignificant influence on force. The force increases slightly with increasing depth of cut and decreasing barrier angle. This shows that rock with low hardness did not give any significant effect towards the cutting force acted on it. The cutting parameters optimization was conducted in the last stage of the study using design expert software to achieve optimum performance of a single PDC cutter. In general, it is desirable to minimize cutting force to minimize the negative effect on PDC cutter. For cartridge marble, the software proposed 5 solutions to achieve minimum cutting force. Based on the provided table, the selected solution gives the highest desirability of at 0.5 mm depth of cut and 15-degree barrier angle as compared to other combination of parameters. The contour plot illustrates the optimal working regions based on cartridge marble cutting. It was observed parameters that falls in a region that has red color give the highest desirability and optimum condition, while the parameters in the blue region are where the parameters did not meet the proposed criteria. For Indiana limestone, 17 solutions were proposed but only 5 solutions were presented. It can be observed in the table that the combination of 0.5 mm depth of cut and 15-degree barrier angle with the highest desirability was selected. A similar trend of contour plot also found for Indiana limestone cutting. In conclusion, 2 main findings were obtained following the objectives of this study. First, we successfully evaluate the effect of cutting parameters on cutting force using different rock types. Meanwhile, the second objective was also achieved by using design expert software to indicate the optimization of cutting parameters towards cutting force. A combination of 0.5 mm depth of cut and 15-degree barrier angle was suggested as the best combination of cutting parameters in obtaining minimum cutting force for both cartridge marble and Indiana limestone respectively. I think that's all for me. Thank you and have a good day.
Okay, thank you very much, everyone, for listening the presentation. I hope you all enjoyed this amazing presentation. So let's take questions if we have any live Q&A. Okay, actually, we have a technical issue with the presenter. First, we'll move to our next presenter. Then later on, if the problem solved, we will go back to our previous presenter. We'll take the question from him. So let's go to our next presentation. Our next presenter is Mr. Muhammad Hamad Rasool from University Technology Petronas. Mr. Hamad will be talking about the influence of alkyl chain length in ionic liquid-based drilling mud for rheology modification. So let's welcome our presenter.
Greetings everyone. My name is Muhammad Hamad Rasool and I am from University Technology Petronas, Malaysia. And the topic of my paper is influence of alkyl chain length in ionic liquid-based drilling mud for rheology modification. And this is going to be a mini review. Let's talk a bit about the introduction and background of this mini review. So we all know drilling field design is the heart of the whole drilling process, and we add different kind of additives into the drilling mud to enhance its geological as well as its filtration properties. So lately, ionic liquids are being used as drilling fluid additives. They possess strong electrostatic force of attraction due to which they interact with clay, changes its structure, and eventually modifies its rheological as well as filtration properties. So ionic liquid are tunable solvents, they have no vapor pressure, and they are liquid at room temperature. So ionic liquids are mainly comprised of a cation and anion. While anion can be any halide or some organic, inorganic molecular ion, while cations are usually the side alkyl chain. For example, azoleums, alkyl phosphates, or alkyl sulfones. So the change in this alkyl length increases the hydrophobicity and polarity of the ionic liquid, which manipulates the behavior of ionic liquid in modification of the rheology as well as the filtration properties. This is the structure of this mini review. I'll be talking a bit about the traditional drilling fluid properties, the chemistry of ionic liquid, then ionic liquid as drilling fluid additives, then effect of ionic liquids on de-spacing of drilling mud, and then I'll be concluding this paper. So when I talk about drilling fluid properties, yield point and plastic viscosity are the very important factors when we consider mud rheology. So yield point is the internal resistance to flow. It is measured in pound mass per 100 feet square. It should be high because if we want better carrying suspension and transportation, but if it gets too high, we are going to have exceptional pressure losses and increase in ECD, and this is something we do not want. Similarly, if we talk about PV, it is just a measure of solid content in the mud and it should be as low as possible. Now, if we talk about the other drilling fluid properties which comprise of its filtration behavior, so mud cake is a solid portion of the mud that deposits on the wall of the wellbore. We want mud cake to form, but if it gets too thick, it is going to cause problems like mud pipe sticking, which eventually leads to the problems like wellbore instability. Now, if we talk about filtrate loss, filtrate volume, or just filtrate, it is the liquid portion of the mud that invades the formation and will eventually lead to the formation damage. So, filtrate loss should be as less as possible, just like the lesser mud cake thickness. So, ionic liquid, as told in the introduction, they are tunable solvents. They are comprised of cations plus anions. Cation are mostly side chain alkanes, and there are thousands of combination of alkyl chains or ionic liquids are possible by the combination of anions and cations. Now this is the comprised review of ionic liquid as drilling fluid additive. This is a mini review because there hasn't been much work done in which ionic liquids have been used as drilling additives. This paper includes most of the paper in which ionic liquid has been used as drilling fluid additives. There is a different review paper. In our previous work, we have published the effect of ionic liquid on cutting transportation ability of the mud, in which we have reported the detailed drilling mud composition, the YPN series for the detailed properties of those ionic liquids and their properties of the mud. Our previous paper can be reviewed. But in this particular mini review, we're just focusing on analyzing the effect of alkyl chain length on drilling field properties such as yield point, plastic viscosity, mud cake thickness, and filtrate volume. If you look at this picture, the comparison has been drawn among the ionic liquids which have been used in the same conditions such as water-based mud with nearly the same formulation and have the same kind of anion, so that the conclusion that is drawn can be more rational and logical. So if you look at this trend, the higher alkyl chain length will result into the lower value of yield point and plastic viscosity. Similarly, higher alkyl chain length will result into more improvement in mud cake thickness and filtrate loss. So what is the reason behind this? To understand this, we need to understand the inherent structure of sodium bentonite. So in sodium bentonite, there is an edge to face orientation where edge is attracted to face and they form a special structure which is called a house of Cole structure. And due to this particular house of part structure, this grants special properties to the drilling mud or drilling fluid, such as its yield point, plastic viscosity. So this structure is going to manipulate those properties. But when we add ionic liquid into the drilling mud, so especially now if we talk about the longer alkyl chains, so the longer alkyl chains, they have higher surface area and they have high hydrophobicity. So they're going to attach on the sodium bentonite surface due to hydrophobicity and showing the electrostatic interaction. So what's going to happen? This will prevent the edge to face orientation to form, which resembles the microstructure of sodium bentonite dispersion and which will result into the lower yield point and plastic viscosity values. Similarly, this particular ionic liquids will alter the wettability of clay, which changes its filtration properties. So longer alkyl chains relatively induce lesser polarity. So though alkanes are usually non-polar, but when they become the side chains, we can compare the polarity of longer alkyl chain on the smaller alkyl chain. So what we need in ionic liquids, they should be hydrophobic and they should show fluoride. Similarly, in this particular portion, we want to see the effect of alkyl chain length on despacing of drilling mud. So whenever any is added in the drilling mud, it tries to intercalate between the aluminosilicate layers of the clay. So similarly, if you see, if the ionic liquid is added into the dry drilling mud sample or the dry sodium bentonite, it will try to increase and enhance the despacing. So despacing is just like the interlayer spacing. The concept is a bit different though. So this particular increase means that there is a successful intercalation, and from this table it can be seen the longer alkyl chain will result into the more intercalation, and that will prove that longer alkyl chain are more successful in sweeping water from the aluminosilicate layers and taking its place. So conclusion can be drawn, ionic liquids are successful drilling fluid additives that improves the rheology and the filtration properties of the mud. Longer alkyl chains are more successful in intercalating between clay layers due to high hydrophobicity as compared to the smaller alkyl chains. So in this particular review paper, we studied the behavior of cations on rheology and filtration properties of the mud. The same review or the same study can be done to study the properties of anion, that how do they manipulate the behavior of ionic liquid as drilling with additives. So this was all for today. If you have any question, the floor is open. Thank you.
Okay, thank you very much, Muhammad Hamad Rasul, for your nice presentation. So I hope the audience have enjoyed this amazing presentation. Now let's take some questions from the audience. So, okay, from the audience, so far we don't have any question. Let me ask one question to you, Hamad. So, can we know what are the limitations of your research?
Um, Hello, good afternoon, everyone. So I want to know, am I audible?
Yes, yes,
Uh,
yes. We can hear you. You can please through it.
All right. So about the limitation of this research work. So basically, in this mini review, I focused on the cationic portion of the ionic liquids. But as we know, that ionic liquids are comprised of a cationic portion and anionic portion. So in this particular review paper, we are only focusing on the side alkyl, which comprise of the cationic portion of the ionic liquid. This is also something we have put in the recommendation part of this particular paper as well. For the future studies, since ionic liquids are also have an ionic portion, and this ionic portion also have a great impact on the properties, on the hydrophobicity and polarity. So in the future research, a similar study or a similar review can be conducted to see the effect of an ionic portion of ionic liquids on changing the rheology and filtration behavior of the drilling mud. I hope this answers your question, sir.
Okay, Hamad, thank you for your answer. My next question to you is why the mud rheology improvement is important to be considered for the oil and gas drilling operations?
Basically, drilling industry or petroleum industry as a whole is all about like economics, right? We want to optimize all the functions and operations, no matter if it includes in drilling engineering, exploration, or production. And when it comes to drilling engineering, we know that drilling fluid design is the heart of the whole drilling process. And we will talk about the drilling fluid design. The one thing that we need to take in consideration is the mud rheology, because it is the mud rheology that is going to decide what is going to be the cutting transportation behavior, what is going to be the wellbore stability, how is going to be the mud filter cake and mud cake thickness. So this is the primary step. The mud rheology decide that is going to kind of decide all the future or all the performance of your mud and how your whole drilling operation is going to be carried out. So it is really important. We have to optimize our mud rheology according to the formation or the type of area that we are drilling in. So that's why we need to focus on mud rheology.
Okay, good, Hamad. We have a few questions from the audience.
Sure.
Let's take the question from the audience. The question is, what is the difference, a different compare with the other study? How would you think your what you can say, the research you conducted is a bit different than the other studies already been conducted?
Okay, so basically this is a mini review, and there hasn't been one review on the basis of the best of my knowledge that incorporates the a comprehensive study on the effect of ionic liquids on drilling meteorology. So I believe this is the only review that you will find, according to the best of my knowledge, that will incorporate and will tell you how can you customize and choose the right type of ionic liquid for customizing the property of drilling mud and customizing it according to your own drilling mud geology need. So this is how I believe that my particular research is different from the previous work, as I believe it is novel and it hasn't been done before.
Okay, thank you again, Muhammad Hamad Rasul, for answering all the questions and for the great presentation.
Pleasure
It
to be
was a
here, sir.
pleasure to have you with us. Thank
Pleasure
you.
is mine, sir. Thank you so much, sir.
Okay, the next presenter is Mr. Imtiaz Ali from University Technology Petronas. Mr. Imtiaz will be delivering his speech today on the title of experimental study on water-based mud, investigate rheological and filtration properties using cupressus cones powder. So please welcome Mr. Imtiaz Ali.
Hi everyone, my name is Imtiaz Ali and I am a PhD student in Petroleum Engineering Department at University Technology Petronas. I would like to thank the conference committee for accepting the work to present here. Today I am going to present this paper titled Experimental Study on Water-Based Mud, Investigate Rheological and Filtration Properties Using Cupressus Cones Powder. I have divided my presentation into 5 sections. Firstly, I would discuss a bit about the background, followed by the objectives of the current study. Thirdly, I will explain about the materials and methodology I have used. Then I will discuss about the results obtained from lab experiments. Finally, we'll conclude my presentation with some recommendations. Drilling fluid is basically a mixture that works as a circulation medium, and a properly designed and maintained drilling fluid system performs various essential functions which prevents the anticipated issues during drilling a well and ensure a successful drilling operation. The most critical issues associated with the muds are pipe sticking, borehole instability, improper borehole cleaning, and failure of cuttings, transport, and so on. In order to minimize expenses and ensure an efficient drilling program, drilling mud's properties should be maintained continuously in drilling operations. And for optimum drilling fluid properties, various additives are added. The cost of the drilling fluid is one of the largest investment costs in the whole drilling process, and it's roughly about 5 to 10% of the total cost of a well. Moving on, the mentioned challenges can be minimized if the mud is properly designed, having the optimum properties. Suspension capability and excessive fluid loss are the 2 key shortcomings of the drilling mud, especially for the water-based mud. These are the 2 main issues. And various additives are added into the mud system to improve these properties. And due to the environmental concerns and these additives are preferred, the bio-based additives are preferred to be utilized in the mud systems. And to date, various agro-materials have been used. Some of these are listed here, like starches, including corn, cassava, potato, and some grass and grass powders, date pits, and wood powder, etc., have been used as a fluid loss and rheology improving additives. This slide is showing the mud complexity with depth. As the well depth is increasing, mud complexities also increases, and thus more and more additives are required to be added into the base mud for their specific for those specific functions. These are some of the most important additives used during drilling operation. Moving to the objectives, the first objective of this work is to formulate the formulation of water-based mud reinforced with an eco-friendly additive, namely micronized cuprous cones powder, and to examine the rheological and filtration characteristics of the formulated mud at standard conditions of temperature and pressure. These are the materials we have used in the current formulation. Cuprous cones as a rheology and filtration control agent, and bentonite is a primary viscosifier. Octanol 1 was used as a defoamer. Barite was used as a wetting agent, and potassium hydroxide as a pH adjustment agent, and fresh water was used for the mud blends. On the right side, the flow chart is showing the procedure for collecting the micronized cuprous cones powder. First, the raw cones in fresh form were collected, followed by the O1 drying at 80 degree centigrade for 16 hours to remove the moisture. And the dried cones were ground for about 20 to 25 minutes to form micro-sized particles of CCP, cuprous cones powder. After grinding, it was dried again in the same oven at the same temperature for more 12 hours to completely to have completely moist powder of the CCP. This picture is showing that how we collected the samples, and the entire lab procedure has been explained here. The table at the left side is showing classification of particle sizes, and the studied powder size is lying in the fine category of particles, that is 74 to 47 to 74 microns. And on the right side, the table is showing the mud formulations, which additive we have been used in this current work. Bentonite was used as a 13 gram, 13 ppb, and CCP was varied from 1 to 5.5 ppb. The muds muds were formulated using API standard practices for lab testing, and for rheological parameters including plastic viscosity, apparent viscosity, and yield point. These Bingham plastic model formulas has been used. In this section, the readings that were obtained from the experimental work are presented in detail for the reference fluid and the different concentrations of CCP. The figure is showing the effect of CCP on the mud weight of the tested samples. It shows that mud weight has not been significantly affected with increase in CCP amount. The base mud showed a bit lower mud weight as compared to the muds with CCP concentration, and the justification behind this insignificant reduction in the mud weight with CCP addition was the development of the foams in the mud, and this issue was noticed during the lab experiments. This figure is showing the effect of the bio-based additive CCP on the pH of the tested muds. Similar to mud weights, no significant changes have been observed with the addition of CCP when compared with the base mud. Only a small increase in the value has been noticed. These two figures are showing the marsh funnel viscosity and apparent viscosity. The response is showing an increasing trend when the CCP concentration has been increased, it is due to the addition of the more and more solids into the system, which creates extra resistance into the flow. And likewise, all other rheological parameters, including plastic viscosity, yield point, were also improved with the CCP amount was increased. The increase in yield point indicating the enhanced cutting transport efficiency. The plastic viscosity is basically, it relates to the resistance to flow due to the interparticle size and the shape of the added solids and the viscosity of the continuous liquid phase. And from the literature, it has been observed that the fine particles showed better plastic viscosity compared to coarser particles in the mud. That's why the particles have been first grinded into micro-sized. The fluid loss is the fluid loss volume is one of the most important factors need to be considered during the design of a mud. It is clearly seen from the figures at the left side that the CCP resulted in the reduction in the fluid loss when comparing with the reference fluid at the extreme left. In addition, both the additives provided a thin and impermeable filter cake as compared to the reference fluid at low pressure and low temperature conditions. And on the right side, it shows the response of the CCP and the filter cake thickness, and it's showing a linear relationship between fluid loss because when the fluid loss is high, the filter cake thickness will also be more. So it's showing a linear trend, and the cake thickness has also been reduced, and we got a slick and smooth filter cake. To sum up, an environmentally friendly and mud additive for rheological and filtration characteristics were fabricated, and the material is a biodegradable and a non-toxic material. This plant is available everywhere and most of the part of the world, especially in Asian countries. And the CCP has the ability to improve the rheology of the mud and control the filtration loss that is frequently encountered in drilling problems in drilling operations, and provided a better and impermeable filter cake when comparing it to the reference fluid. It is further recommended to test it in high pressure and high temperature conditions, and as well as other sizes should also be considered for these properties improvement. Thank you so much.
Okay, thank you very much, Mr. Imtiaz Ali, for a nice presentation. I hope everyone enjoyed this amazing presentation. Now let's take some question from the audience, right? So one of the question is how the rheological behavior of the drilling fluid would be, you can say, playing its role for the cutting transportation. How would you say that the rheological properties are playing a role for the cutting transportation?
Actually, for cutting transportation, we are considering.
Yes, we can hear you. Please
Yeah.
continue.
So the basic, there are two major, shortcomings for the water-based mud. The one is suspension capability, and the other is the filtration capability. So this is related to, your question is related to suspension capability, and cutting transport is one of the problems. So what we are doing, basically, we are optimizing the yield point of the mud by using some special additives that have gelling properties. So what basically it does, it changes, it has some yield point, and we are considering two things basically. If we go to the modeling side, so the K and the consistency index and the flow behavior index. So the consistency index is increasing, and
for the same time the n is decreasing, and that's basically contributing for the better cutting transportation.
Okay, you just said you are going to optimize the yield point, right? Can you give
Yes.
us any optimum value of the yield point that you can say that will be the industrial standard we have to follow? So,
Yeah.
in comparison, as you can say, we want to compare with the industrial
Yes.
standard. Can you give us
Yeah.
any value?
For the lab work, we have API recommended values, and for the water basement, it's starting from 17 to 50, 55. Some and there is, there different, stated somewhere like 50 to 52, from 17 to 50 or 52, and another here is from 27 to 50
Okay,
pounds
okay,
per 100 feet square.
okay. Imtiaz, as you said, you give us some industrial standard. If I say increasing yield point and increasing plastic viscosity, is this in our favor in terms of the cutting transportation or not?
No, not always, because too much plastic viscosity will not give you the better results for yield point.
Okay, okay. Thank you, Mr. Imtiaz Ali, again for answering all the questions very well and for the great presentation as well. So
You're
it
welcome.
was a pleasure to have you with us. So hope to see you again. Thank you.
Pleasure.
Okay, we have our next presenter. Again, Mr. Muhammad Hamad Rasul from University Technology Patronas. Mr. Hamad will be talking about the rheological characteristics, the characterization of potassium carbonate deep eutatic solvent based drilling mud. So let's listen Mr. Hamad Rasul on his research.
My name is Mohammad Hamad Rasul and I'm from University Technology Petronas, Malaysia. The topic of my paper is Rheological Characterization of Potassium Carbonate Deep Eutectic Solvent-Based Drilling Mud. So let's talk a bit about the introduction and background of this paper. So lately it has been seen that ionic liquids are successfully used as drilling fluid additives for rheology modification and also to improve its filtration behavior. So ionic liquids show strong electrostatic force of attraction. They interact with clay, changes its structure, and ultimately change its drilling fluid properties. So recent research has shown the most popular class of ionic liquids, the imidazolium-based ionic liquids, they are toxic and generally they are found to be non-biodegradable and they are really costly and expensive. So we need an alternative that is non-toxic and that is cheaper in real sense, and the alternative should possess the same properties as possessed by ionic liquids. So deep eutectic solvents are considered as fourth generation ionic liquids and they are non-toxic and cheaper alternative of traditional ionic liquids. So ionic liquids show the strong electrostatic force of attraction, but the force of attraction that is present in DES is hydrogen bonding. So just like ILs, DES also interact with clay and changes the drilling fluid properties. So in our previous study, we used potassium carbonate and glycerol-based DES to see the effect on rheological and filtration properties. And we found out that the addition of DES, especially the potassium carbonate-based DES, improved the YP over PV ratio, which is an important indicator of mud rheology, to the optimum range of 0.75 to 1 pound mass per 100 feet square per CP. We also found out that the addition of DES caused 36% decrease in mud cake thickness and 24% decrease in filtered volume. Now, in this current study, we want to understand the underlying mechanism behind the working of DES as a rheology modifier. So for this, we have suggested some structural characterization, and these characterization were suggested based upon this question. We wanted to see which mineral of the clay, because clay has a lot of mineral like alumina, silica. So we wanted to see which mineral will show more affinity towards DES. So in other words, this interaction will prove that DES has interacted with clay. We also want to see what will be the effect of DES on de-spacing and size of clay. Also, what will be the effect of DES and on the particle size distribution? Lastly, what will be the effect of DES on stability of collider? In this particular research, we are also doing rheological modeling. These rheological models are very important because they are significant to simulate the behavior of drilling mud in dynamic conditions. So if we talk about materials and methods, so for Fourier transform infrared spectra, we have used Perkin-Elmer. For BES water-based mud, which was prepared under API 13B1 guidelines, and for XRD, we have used wet drilling mud samples and we have used X-ray for operating at 45 kilovolts and 40 milliamperes with a copper alpha radiations. And for PSD and zeta potential, we have used Mol1 zeta sizer nano ZSP. And for rheological modeling and the shear thinning behavior, we have used rheometer DH-R1, which has been used to find the shear stress and dynamic viscosity of DES water-based mud at shear rates between 1.48 per second to 1200 per second at 25 degrees Celsius and 100 degrees Celsius. There are three more most important models that are used in drilling fluid industry. Brigham plastic model, Gill power law, or Herschel-Buckley model, which is also termed as YPL. So we will do curve fitting, and the curve fitting will be done based upon these parameters, the mean percentage error and the standard. This is proved by the results of FTIR. So from the fingerprint region of alumina, it can be seen the change in wavelength refers that DES has interacted with the alumina present in the clay. So this proves that DES has successfully interacted with clay. So there was a force of attraction. So the result of XRD proved that DES has successfully intercalated between clay layers. You can see for the hydrated sample, the addition of DES in the hydrated drilling mud study, the D-spacing will keep on decreasing. And for the results of discussion for particle size distribution, so for the filtrate thing, the PSD is very important, and especially in PSD, the concept of D10. So D10 is telling us the amount of a percentage of particle whose diameter is less than these particular values. So from PSD it can be seen the addition of DES is decreasing the amount of fine particles present in the DES water-based mud. So the concept of zeta potential is basically telling us that how stable is our collider is. So if the value is greater than 30 millivolt, so collider is considered to be very stable. It's considered to be stable. As the value goes on increasing, the stability will go on increasing as well. So we can see our 0.5% DES is the most stable collider. So now let's talk about all this mechanism and discuss what is actually happening. So you can see in this picture for the dry sodium bentonite that D spacing is 12.64 Armstrong, which increased with the addition of water. And when DES was added in drilling the slurry, the D spacing kept on decreasing. Similarly, from Scherer equation from XRD analysis, we have found the average beam size, which showed that the addition of DES decreased the particle size in average manner. So this is something that we have included in our research to understand the mechanism of filtration as a function of fine particles and the size of particles and particle size distribution. So these are four different scenarios in which it can be seen when we have smaller grain size in general and lesser percentage of fine particles, we will get thin mud cake and smaller invaded zone. So this invaded zone is formed when we have very small fine particles, and these small particles will even invade to the small particles and they will increase the area of invasion. This area of invasion will cause a pressure differential and will increase the filtrate rate. So in our study, we have found out that sodium bentonite has a face-to-edge orientation, and this orientation is disassembled when we add DES into the mud. So from the result of XRD, it can be seen that our DES has successfully intercalated between the layers, which changes its structures and improves the rheology of the mud. Similarly, From the particle size analysis, it can be seen that like smaller particle size will have lesser permeability, so the infiltration properties will be improved. Similarly, the DES, and from the particle size distribution analysis, it can be seen the addition of DES decrease the fine particles. So decrease in fine particles mean the filtration rate will be decreased because the area of invasion will be decreased as well. So we can see the attachment of DES on the clay will also change its wettability, which also will have an effect on the filtration properties of the mud. So we for the rheological modeling, we consider all the models and we studied them at 25 degrees Celsius and 100 degrees Celsius, and we found out the base sample follows power law, while our DES base mud at both temperature, even at elevated temperature, follows Herschel-Buckley model. Herschel-Buckley model is the best model because it incorporates the flaws that are present in power law. That is, that it will incorporate the yield strength at even zero shear rates. So this is the shear thinning behavior. It can be seen. Our DES base mud showed excellent shear thinning behavior even at elevated temperature. So, in conclusion, potassium carbonate improves the mud rheology by intercalating between clay layers, and the filtration properties are improved because DES decrease the average size of the particle, which decrease the permeability and improve the filtration properties. And DES also decrease the distribution or the percentage of fine particles, which decrease the area of solid particle invasion, which in turn improves the filtration properties as well. And RDS shows excellent shear thinning behavior and follows Herschel-Buckley model. So this is it for today's presentation. If you have any questions, the floor is open for questions. Thank you so much.
Okay, thank you very much, Muhammad Hamad Rasul, again to be a part of this parallel session. So I hope everyone has enjoyed this amazing presentation. So now let's take some questions from the audience. So the first question is, uh, what is the screening criteria for the DES?
All right. So basically, in this study, we have chosen the potassium carbonate-based DES, and it wasn't like just chosen out of nowhere. So my screening criteria was based upon like five different parameters. Number one being total hydrogen bond counts, because what actually happens, we know DES is composed of a hydrogen bond donor and a hydrogen bond acceptor, and both of these species have a special number of hydrogen bond count. So this was in my list, and second one being the availability of raw materials. Third one being its pH, then its thermal stability. So based upon the combining all these particular parameters, I have sorted this particular DES out because it has a high number of hydrogen bond count, which means it will have a very good capability to form hydrogen bond with the clay. And second one being it has a good thermal stability. So it makes it this will make it a good candidate for high temperature wells as well.
Okay, Hamad, what are the limitations of the DES if you consider it inside the drilling mud?
Uh, so basically, as I was talking about thermal stability of this DES, so this particular potassium carbonate DES, we subjected it to thermogravimetric analysis to study its thermal stability. And we found out that up to 150 degrees Celsius, this particular DES as a whole and its raw materials are very stable. They won't start decomposing. So, according to the literature and everything, we know the temperature of high temperature wells is up to 150 degrees Celsius. So, it makes an excellent candidate for high temperature wells. But after 150 degrees Celsius, you cannot use it for ultra high temperature wells or super ultra high temperature wells. So that's where the limitation occur. You cannot use it more than for 150 degrees Celsius. But for a high temperature well, this DES is an excellent candidate because this is going to modify your rheology, and modifies in that sense, it is going to improve it. It is going to improve your filtration behavior, and the best thing is it is very cheap, environmental friendly, and it is biodegradable as well. And this is something that we can find in the safety data sheet of this particular DES as well.
Okay, Hamad, how can you say that the DES is performing better than the ionic liquid? In what
Uh,
term, in what sense you can say that?
Basically what we did, this paper is basically a part of my thesis, right? So we have also I have also kind of conducted experiment using three best ionic liquids. So I have done the literature review and I sorted out three best ionic liquids that gave the best results in terms of rheology and filtration behavior. And I kind of like performed all the experiment using those ionic liquids as well, and I found out my DES performed better than these three ionic liquids. And then I compared not just their performance, their cost, their environmental toxicology from their safety data sheets, and I found out those three ionic liquids are just not costly and not easily available, but they are not environmental friendly. Their EC50 values are very high, and the safety data sheet explicitly says they are not biodegradable. At the same time, I made a comparison of the raw materials of DES from their safety data sheets, and I found out the raw materials of the DES that I have used, they are very biodegradable, like readily biodegradable. They are very cheap and they are not toxic to aquatic life. And this is something that is mentioned very vividly in the safety data sheets of these chemicals.
Okay, thank you very much, Hamad, again
Pleasure to be here,
for
sir.
your great answers to all the questions and for the great presentations.
Thank you, sir. Pleasure to be here.
Okay, it was a pleasure to have you with us. Hope to see you again. Thank you. Okay, our next presenter is Mr. Kawamina Ainu from University Technology Petronas. He will be talking about the evaluation studies of KCl and amino acid mixture for clay stabilization and rheological enhancement of water-based fracturing fluids. Let's welcome Mr. Kawamina for the presentation.
Ladies and gentlemen, my name is Kweno Kwamina Atul, and I'm here to do a presentation on the topic Evaluation of KCl amino acid mixtures for clay and rheological stabilization of water-based fluids during hydraulic fracturing processes. Now, this will be the order of my presentation, starting from the introduction, which discusses the need for producing from unconventional resources, the challenges with the exploitation, through to the work, and then the recommendations after the study. Of all the existing fossil fuels utilized for energy, natural gas is considered the cleanest of them all. Thus, there's an increasing demand for the use of natural gas for commercial and industrial purposes. However, the conventional sources of these natural gas and all these fossil fuels are depleted. Thus, there is a need to balance the supply of natural gas by looking or producing from unconventional sources that have not yet been explored. There are several of natural gas that have not been explored. Some of the alternative sources we have are the gas hydrate, we have the coal bed methane gas, and then we have the aquifer gas. However, the focus of my study will be on shale gas. Shale gas is typically a type of natural gas that is present in a shale formation. For a typical shale formation, it contains the organic matter that thermally matures at the right conditions to produce the natural gas. However, it also contains certain minerals like clay minerals, like non-clay mineral. Malaysia is known to have an estimated hydrocarbon initially in place of 8.8 trillion cubic feet of shale gas resources. However, the issue with exploring shale formation is that shale is naturally tapped. The pores of shales are not connected, thus producing from such formations are considered very, very expensive. Thus, there's a need to apply special technologies in order to improve their production from shale formations. The special technologies that were employed were the use of horizontal drilling and then hydraulic fracturing with water-based fluids. Now, when these processes or these technologies are employed right on the shale formation, it will lead to the production of methane gas from the shale formation, which will lead to the production of clean energy. However, one challenge is known to arise during the use of these technologies on the shale formation. The water-based fluids that is used for the application of these technologies, they tend to react with the clay minerals present in the shale formation. This reaction leads to the swelling of the clay. Then if the clay swell, it tends to plug the shale formation, causing it to become tight, then going back to the issue of low recovery all over. Several solutions have been suggested in order to combat the swelling of clay formation. However, the chiefest of them all is to continue the use of water-based fluids. This because the water-based fluids are considered cheaper and because they are also non-toxic when compared to the oil-based fluids and the other fluids that are utilized, because water-based fluids are considered cheaper and non-toxic. However, to continue the use of the water-based fluids, researchers suggested the introduction of clay stabilizers to make the fluid a stabilized water-based fluid. The presence of these clay stabilizers would limit the swelling of the clay formations present in the shale during drilling or hydraulic fracturing processes. There are two main types of clay stabilizers utilized presently. We have the inorganic salts such as KCl and then sodium chloride and then the chloride salt, and then we also have organic compounds. Some little facts about the clay stabilizer. For the inorganic salts, they have shown strong swelling inhibition potentials. They limit swelling significantly. They're also less expensive and their inhibition mechanism is also very strong. However, they're only effective when utilized under high concentration. However, research has shown that the use of chloride salts at high concentration tends to affect it, are very toxic and tends to affect the ecobalance of the system. Moreover, the use of these inorganic salts tends to affect the rheological properties of the fluid. For the organic clay stabilizer, they also displayed strong swelling inhibition potentials. Their inhibition mechanisms are stronger than the inorganic salts. However, the issues with the organic clay stabilizers is that they have large molecular weight. So because of their large molecular weight, they tend to clog the pores of the shale formation, reducing the permeability of the shale formation, and they're also expensive. So the rising trend presently in literature is actually to combine mixtures of the inorganic salts and the organic clay stabilizers at suitable concentration to avoid the issue of high toxicity and then reduce the cost. However, with the research gap, most of the combinations that have been done with these polymeric organic compounds, which are considered expensive and which also have high molecular weight. However, monomeric organic compounds have not been combined together with the inorganic salts. Amino acids are monomeric organic compounds that have displayed suitable clay stabilizing properties. However, no combination studies have been done using inorganic salts and amino acids together. So the objective of this work is to evaluate the inhibition potentials of mixtures of KCl and amino acids using the linear swelling test, and then evaluate the effect of these mixtures on the rheological properties of a typical water-based fluid. So for the methodology, these are some of the materials that were utilized. We use certain materials to prepare an hydraulic fracturing fluid, then the linear swell meter and the rheometer as equipment to utilize. And then for the objective one, so the objective one, which is the linear swelling test, we prepared clay wafers as shown in the diagram using the hydraulic compactor. Then we immerse these clay wafers into the prepared fracturing fluid, and we monitored the swelling percentages using a linear swell meter for 24 hours. Okay, for the objective 2, which is the rheological study, we also prepared water-based fluids with 2 weight percent of the studied chemicals, and for the mixtures we use 1 weight percent each of the inorganic and then the amino acids. Then we performed the rheological testing at varying shear rates from 0.01 per second to 1,000 per second. Then we determined the flow parameters to monitor the effect of the mixtures on the water-based fluid. Okay, so for this result and discussion, first we had to do a validation study to confirm that our experiments are reproducible. So we did a validation studies for the linear swell meter, the base fluid. We compared it to literature, and we realized that the closeness of the curve suggested that the works are reproducible, even so too for the rheometer validation curve also. So for the linear swell result, that for our first objective, we compared the swelling performance of the various fluids in the presence of our amino acids, and then the mixtures also. And we realized that alanine showed a 14% inhibition efficiency, reducing swelling by 14%, arginine by 6%, KCl at 12%. However, for the mixtures of the amino acids, we realized that the inhibition efficiency of alanine when mixed with KCl reduces, whilst the inhibition efficiency of arginine when mixed with KCl increased from 6% to 10%. This suggests that amino acids mixtures with KCl vary differently for each amino acid that are studied. So for the objective 2 also, we also realized that amino acids increases the viscosity of the water-based fluid. We don't just want a chemical that reduces swelling but increases the viscosity of the fluid, and that is what amino acid gives us. It increases the viscosity of the water-based fluids. For KCl, we realize that it rather decreases the viscosity of the water-based fluids. Both extremes, that is the amino acids and the KCl, are not suitable for fracturing purposes. But however, with the mixtures, we realized that they did not significantly affect the flow parameters of the base fluid. Thus, a swelling inhibitor that limits toxicity impacts stable swelling inhibition and stable rheological potentials into a water-based fluid is optimal for hydraulic fracturing processes, and that is what the mixtures of KCl and amino acids gives. As conclusion, this work investigated the efficacy of 2 amino acid mixtures with potassium chloride for clay stabilization during hydraulic fracturing processes. However, this is just a fundamental study, and we noticed that amino acid mixtures with KCl promises a toxic, less hydraulic fracturing process, including a suitable swelling and rheological stabilization processes. Secondly, we realize that the stabilization potentials of amino acid mixtures with KCl varies for each amino acid, thus requiring experimentation for all 22 amino acids. These are some of the recommendations from our study. A wide range of amino acid mixtures with organic salts have not been explored, and we recommend their studies. Then the need to evaluate various concentrations of these mixtures in order to achieve the optimum concentration that produces a synergistic effect of these mixtures. And then lastly, further studies incorporating the diverse borehole conditions, such as the study of pH effect, the study of high temperature effect, and the study of increasing salinity concentrations are all needed. Thank you very much.
Okay, thank you very much for the nice presentation. I hope you all have enjoyed this amazing presentation too. So actually, due to the technical issue, we cannot go with the Q&A session with Mr. Kawamina, right? And he was actually our last presenter too. So with this, we are going to conclude our session. Thank you all for attending the session we have. We hope you have learned and enjoyed all the presentations. See you all in the next parallel sessions. Until then, bye-bye. Assalamu alaikum wa rahmatullahi wa barakatuh.